Okay, here we're going to look at how we're going to calculate the heat for each part of this graph that we looked at yesterday. So just as a review, this is a temperature versus time graph, and we're looking at ice. The ice starts out at maybe -10, maybe -20, some number down here less than 0. It is staying in ice form until it gets to 0 degrees Celsius. At this point it starts melting, having a phase change where the temperature remains the same as time passes, and all of the energy in the system is being used to change from a lower state to a higher state of matter. And then after all of the ice melts, we've got the increase in temperature in water, and then we start vaporizing at 100 degrees here. All of the energy here is being used to change state from water to steam. And then after all of the water is evaporated, we start increasing temp again after 100 degrees. Okay, so we saw two equations yesterday. The one in blue, Q, which is heat. Heat is equal to mass times specific heat, Cp, times the change in temperature, which is final minus initial temperature. Make sure you're careful of your negatives here whenever you're dealing with this part of the graph. And the second equation is Q equals mass times latent heat. And that's going to be the red sections where we have phase changes going on. Because in these sections, the red sections, there is no delta T, no change in temperature. The change in temperature is only in the blue sections. Okay, so with L, this L, latent heat, we have two types of latent heat. We have the latent heat of melting. This is technically called the latent heat of fusion. But to simplify this, since I am not around, and this is having to be kind of condensed, we're going to be calling it the latent heat of melting, and then the latent heat of vaporization. So the L, latent heat, in the red equation on the red section, Lm is the latent heat of melting. We're going to use that latent heat in this section. Or Lv, which is the latent heat of vaporization, we're going to use that in this section here when we're evaporating from water to steam. Okay, the other thing that you're going to need is all of this info here. All of these numbers would be different for different substances, but we're only going to be working with water for this piece of today. So we have Cp. Remember, Cp stands for specific heat. The specific heat of ice, this section, specific heat in blue, ice in blue. The specific heat of ice is 2090 joules per kilogram degree Celsius. Cp of water, specific heat of water, in this section here, see there's a little Cp right there, that's where you're going to use that. It's 4186. Cp of steam, the specific heat of steam, is right here in this section, Cp. Latent heat of melting, which you'll use whenever the melting is happening, 3.33 times 10 to the 5th joules per kilogram, and the latent heat of vaporization here in this part when we are evaporating is 2.26 times 10 to the 6 joules per kilogram. I'm just going over everything that you're seeing here. This would be a good spot maybe to take a screenshot or pause or just repeat all of that. But this is just all of the information you're going to need to use when you go over here and start doing your calculations. So there's two formulas that we're looking at, and it's going to be two different processes that you're looking at. So you are either going to be dealing with and calculating from your word problem, it's either going to be talking about a phase change section of the graph, or the word problem will be talking about a temperature change section of the graph. So if it's talking about a phase change, if the for the instance, this one, number 1, says calculate the heat required to melt 8 kilograms of ice. So I know I'm melting ice. Melting ice is happening right here in the phase change. I remember from yesterday that whenever something is melting, the temperature is not changing, it stays the same. So this is talking about a phase change. There's no temperature change listed here at all. Number 2 is talking about a temperature change. Number 2 says calculate the heat required to raise the temperature. So we're having a temperature change here. Raise the temperature of 6 kilograms of liquid water, or just water, from 15 degrees Celsius to 50 degrees Celsius. So how much heat do I have to put into the system to raise the temperature from 15 degrees Celsius up to 50 degrees Celsius? How much heat does that require? So here, your clue is your temperature change. We have an initial temperature, we have a final temperature. So I know this problem is asking me, it's talking about a temperature change, which would be the blue equation that has delta T, versus your phase change questions, which will say either melting or evaporating. If you see melting or evaporating, you know you're going to look at latent heat, because the latent heat is the heat energy used here and here for melting and vaporization to change states. All the energy is being used to change states. It's not being used to change the temperature. So two types of problems, either a phase change or a temperature change. All right, so once you decide which type of problem you're looking at, you're going to, that'll tell you which equation to use. Number one, calculate the heat required to melt 8 kilograms of ice. I started with my variables list. Mass is 8 kilograms. And I know I'm melting in this section, so melting, I'm going to use latent heat. And my latent heat for melting is 3.33 times 10 to the 5th. My equation for a phase change equation, that's all the red. Phase changes are red. Q equals ml, and I'm just multiplying my mass times my latent heat. If I'm working with a problem that's talking about a temperature change and I'm calculating the heat to change the temperature, I'm going to be using the temperature change equation. The heat, which is Q, required to change the temperature of a certain substance. So I have that formula here, my change in temperature formula. I need mass, specific heat, and delta T. My mass is 6. Specific heat is water. So this is where you need to be careful, because there's 3 CPs. One question could say, how much heat is required to raise the temperature of steam? How much heat is required to raise the temperature of ice? Then you would need to use a different specific heat for ice, water, and steam. All right, then I have my initial temperature and final temperature. Initial, I start out at 15 degrees Celsius. Final, I end at 50 degrees Celsius. So I have Q equals M CP delta T. Q equals M is 6. My specific heat of water, 4186. And my delta T is final minus initial, 50 minus 15, final minus initial. Subtract this, multiply by that, and you get the answer here. So when you go and work on your problems today, there's only 5 math problems that you're going to be working out. First, you have to decide, are we changing phase? Is the energy, Q, the thermal heat energy, is the Q being used to change the phase, change the state, or is it being used to change the temperature? Do you have a temperature change or a phase change? And that's going to tell you which of these equations to use.